Hello and welcome to this FMSP online revision recording for the OCR specification module M1 Mechanics. And this topic is Kinematics of Motion in a Straight Line. And looking at the specification, there are 4 points mentioned. The first one is that we need to be sure we understand the concepts of distance and speed as scalar quantities in one dimension, and of displacement, velocity and acceleration as vector quantities. And although it says in one dimension only here, don't forget that the direction, positive or negative, means we do have a direction specified for these quantities, even if it's just along a straight line. Secondly, graphs. Graphs of displacement against time and velocity against time. And particularly when you're looking at the graphs, we have some important facts that we can read directly from the graphs. If it's a velocity graph, velocity against time, then the area beneath represents the displacement and the gradient represents the acceleration. If it's a graph of displacement against time, then the gradient tells us the velocity. The next 2 points then, we can use differentiation and integration with respect to time to find expressions for velocity and acceleration from displacement, or working the other way, find displacement from velocity and acceleration from velocity. And the last point, use appropriate formulae for motion with constant acceleration. It's a short statement, but it means everything you can ever need to do with the Suvat equations. And let's look at those next. Some people refer to these as the UVAST equations, and others simply as the equations of uniformly accelerated motion. And here are the 5, and notice that each equation contains 4 of the variables. Now, a very important point to make straight away is you must make sure that all the quantities are in the right units. So here are the units below, and should you get anything that's in kilometers per hour or some other unit that needs converting, change it first before plugging it into these formulae. The next thing to say is be very careful to choose the right formula. You can see from this table that each formula contains 4 of the variables, so sometimes it's easiest to choose which formula to use by considering which variable isn't required. And as a rule of thumb, only find the variable they're asking you for in the question. Don't find something else first, because that'll make for a 2-stage process, and that doubles your chance of making an error. Now let's look at differentiation and integration. And I've just made a little note here that whereas we use S for distance or displacement, we often see X used when we're differentiating as well. So don't be confused by that. Well, if we take the displacement and differentiate it, so that's ds by dt, that gives us velocity. And if we differentiate the velocity with respect to time, that gives us the acceleration. That's nice and straightforward because there's no trouble about the constant. However, if we're integrating acceleration to find the velocity, we might need to find a missing constant from some initial conditions. The same if we're finding the displacement by integrating the velocity. So look out for simple conditions like initially, meaning t equals 0, or words that more or less mean at rest and therefore v equals 0. Okay, let's do some questions then. So here's one which involves some use of Suvat plus a couple of graphs to sketch. A particle is projected upwards with velocity 5 meters per second from a point 2.5 meters above the ground, and we're asked how fast is it going when it strikes the ground, and at what time does it reach the ground. Then we're going to sketch a couple of graphs to represent the motion of the particle. And straight away I'm thinking, am I going to take upwards or downwards as positive? Well, I want some sort of picture to see what's going on. Our particle is projected when it's already 2.5 meters above the ground. And then it's going to be projected upwards at a speed of 5 meters per second. So my feeling is, let's take upwards as our positive direction. And of course that means that the acceleration downwards, which is the acceleration due to gravity, has to be negative. Okay, so what do we find? We want to find the velocity when the particle hits the ground. And I'm going to list everything I need for this part of the question. Initially, u equals 5 meters per second. The acceleration is the acceleration due to gravity, 9.8 meters per second squared. A warning to you physicists, don't put 9.81. The front of the paper specifies to take 9.8. Now, we want to know when it hits the ground, in other words when it's gone down 2.5 meters from its present position, so that's an important sign to get right. And the first thing we want to know is, how fast is it travelling at that point? So I have V, U, A and S. I therefore don't want to choose a formula that has t in it. And the formula which excludes t is v squared equals u squared plus 2as. Again, a note to physicists. I've often found physics students are very keen to rewrite and rearrange formulas. On this occasion it doesn't matter very much, but I would always say with maths questions using Suvet formulas, substitute the numbers in first before you rearrange, because often one of the numbers you substitute in is 0, and that would make your rearranging easier. Okay, in this case then, v squared equals 5 squared plus 2 lots of a, which is minus 9.8, times a distance which is 2.5 meters downwards, so that's minus 2.5. That gives me v squared equals 25, plus, and calculating all that, in fact it's 49. So I have v squared is 74, and therefore v is the square root of 74. I calculate that to be 8.60 meters per second. So 3 significant figures. Okay, and now let's find the time at which it hits the ground. Now, this much of the information is the same. I shan't write it all out again for time's sake. The one extra thing that we're trying to do now is find t instead. So I want an equation that links u, a, s and t. And my advice is, although we know v, we hope it's correct, don't rely on that answer when we can rely on information we know is definitely correct from the question. So I'm going to use s equals ut plus a half at squared. So s I know is minus 2.5, u I know is 5, so I've got 5t, then plus half of a, well that's minus 4.9, t squared. So that's the equation I need to solve. Well, first of all, I think I'm going to get it all onto the left, so I'm going to add 4.9 t squared to both sides, and take 5t from both sides, and that gives me a quadratic with every term on the left. I'm also, to save making errors with those decimals, going to multiply through by 10. That's not to say you couldn't simply use the equation above and pop it in the formula, but I would just like to look first and see whether or not this whole number formula factorizes. Well, it doesn't. so I'm going to have to put it into the formula anyway. T equals minus negative 50 plus or minus the square root of, well, it's b squared, that's 50 squared, minus 4 times a, which is 49, times c, which is minus 25. I'm just going to do what I normally do and say if I'm subtracting something that's going to be negative, that's all going to come out as positive. And it's over 2a, which is 98. T therefore is equal to 50 plus or minus square root of, now that comes to 7,400. And you can see from the line above that it's the square root of 50 squared plus something. So once you take 50 squared, add something, and then square root it, it's definitely going to be bigger than 50. That means I don't need to consider that negative solution. It's going to give me a negative value for time. So just taking the one solution with 50 plus the square root of 7,400, all divided by 98, I get 1.39 seconds, which to me seems a reasonable time for throwing something up in the air and expecting it to come down and hit the ground. To 3 significant figures as per the standard instruction at the front of the exam paper. Okay, let's consider the graphs of the motions that go with this then. I need to come up with a graph of velocity against time and a graph of displacement against time. And although I've got a fair bit of information already, I'm going to write down on here what I know and perhaps take this a little bit further. Well, if I was considering velocity, I know v equals u plus at, and therefore an expression for v could be 5 for my initial velocity, my acceleration is minus 9.8, t, there we go. And I also happen to know that when v equals 0, looking at that, 5 must be equal to 9.8t. And that gives me a time of 0.510 seconds. The question doesn't ask us to find that, but it's going to help me just understand the situation a bit better, because this is a linear equation, 5 minus 9.8 times t. It's negative gradient, minus 9.8, so it's going downhill. We already knew from the question that we start with a velocity of 5 meters per second. And when the ball is thrown up, there's a moment at the top when the velocity temporarily is 0 before it starts coming downwards, and its velocity is negative, in other words heading downwards, and I've just found that time. It's when t equals 0.510 seconds. Now let's compare that to what we know about the displacement. Our formula is s equals ut plus a half at squared for the displacement, but from where? Just be careful here. Now, initial velocity is u times t plus a half a, well that's minus 4.9 again. But this is from its initial point of projection, which was 2.5 meters above ground level. So what does this equation look like? Well, for a start, it's an inverted parabola, because I have a negative coefficient of t squared, and also when t equals 0, the displacement is positive 2.5, because it started 2.5 meters above the ground. So I'm just going to mark on a point on the axis here, because it doesn't start at 0, 0. It goes up and then comes down. What I'm going to try and do is draw it so that, more or less anyway, this point here happens at the point when the velocity is 0. So there's your point, which is 0.510 seconds. and we've already found out that the time when it hits the ground is 1.39 seconds. And I guess on this graph perhaps we wouldn't see it go below ground level, but I've drawn it in for completeness. There we go then, graphs of the velocity and the displacement. On to another question. This question may take a bit of reading, so can I remind you, if you want to pause the recording and read it at your leisure. Now, a very important point. It's a graph question. It's offered to us as a graph, so don't use SUVAT. That's not to say that you couldn't use SUVAT, but in general, don't use SUVAT for graph questions. Use a graphical method. Use those things we know about area under a graph and gradient. Now there's a lot of information here, and what I want to do is transfer it to the graph and work from the graph. So a car is travelling on a straight road. It accelerates from rest to a speed of 15. We can see that here. In a time 6 seconds, the 6 is marked. It travels at a constant speed, so acceleration 0, that's why the graph is flat, for 11 seconds, and decelerates to rest in 2 seconds. I'll put that information on a copy of the graph in a moment. Then, after this point, the driver gets out, walks back, and that's why the line is below the graph. The -2 means he's walking backwards, or at least walking forwards in a backwards direction. He then is in a shop where we have a displacement, a velocity of 0 for a certain period, which is this part, and then he jogs back at a faster speed, which we're told is 5 meters per second, but we don't know for how long and how far. So we'll work through in order these parts of the question. We want the initial acceleration and final deceleration of the car and the distance it travels, and then to find out how long the driver is in the shop, which basically means filling in the rest of the times. Okay, I've enlarged this part of the graph to make it easier for me to write on the information I want to. The car travels at a constant speed for 11 seconds. In other words, from 6 there's a further 11 seconds, so that must be 17 seconds. And then decelerates for 2 seconds, so this time must be 19 seconds. We're asked, what's the initial acceleration? Well, it's a velocity time graph, or a graph of a velocity against time, a TV graph, as they quote it in the specification. And we're going to get that from the gradient of the first section of this graph. And it's a rise of 15 over a distance across of 6, and that is 2.5 meters per second. Is acceleration meters per second squared. And then we're going to find the final deceleration. The question specifically says final deceleration. I'll come back to that word in a moment. Now, this again is from the gradient, and the height has changed by 15 in a time of 2 seconds. So that's a deceleration of 7.5 meters per second squared. But I want to make a very important point about the sign. It's a negative gradient. If I look at the gradient of this line, the gradient is a change downwards of 15 over a time of 2, which is minus 7.5. In other words, the acceleration is minus 7.5 meters per second squared. If the acceleration is negative 7.5, the deceleration is positive 7.5. It's as though the sign has been incorporated in the word decelerate. And then for the second part, we want the area below the graph for the total distance travelled by the car. Now, it's a trapezium, and my immediate reaction to that was use the formula for a trapezium. It's half times the sum of the parallel sides, 19 seconds at the bottom and 11 seconds at the top, times the width between them, which is 15, which gave me a nice easy half of 30 times 15, and half of 30 is 15, and I happen to know that 15 squared is 225, so that's the total distance. However, it's perfectly reasonable to have looked at the graph and found the separate areas and said, for this first triangle here, it's half the base times the height, half of 6 times 15, that's 3 times 15, that's 45 meters. For the piece in the middle, it's simply the width, 11 seconds times 15, that's 165 meters. And for the final triangle, the base is 2 and the height is 15, half of 2 times 15 is 15, and adding those all together also comes to 225 meters. So again, an alternative, perfectly legitimate method. Now let's go back to the original graph. We know now that this is 19 seconds. What else do we know? Well, we know that he jogs for 20 seconds at 2 meters per second. So this is 20 seconds here, and that must take us therefore to 39 seconds. But if that little rectangle is a width 20 times a depth of 2, that must be an area of 40 meters below the graph, because it's 40 meters backwards to the shop. He's driven a certain distance, parked beyond the shop, and then walked backwards to the shop. Later, when he comes out of the shop, if he gets back to the car, he must also travel 40 meters. And if we're told his height, the height on the graph, which is his speed, is 5 meters per second, then it must mean that the width is 8 seconds. And therefore this point, when he started to jog back, is 8 seconds before 60. That's 50 seconds. The only thing is, having written all that on the graph might not convince the examiner, so I'm just going to write down what I think we should put. Well, first of all, he walks back 20 seconds at 2 meters per second. That scribble is a multiplication sign. And that's 40 meters back to the shop. Then he jogs. And he jogs 40 meters. Well, therefore, we've got to decide that that's 5 meters per second times something, that's clearly 8 seconds, back to the car. That calculation explains where I've got my 8 seconds from. Therefore, having now written those times on the graph, it's clear to see that the time in the shop is simply, and I see my error by the way, that's 52 seconds up there. 60 take 8 is 52 seconds. 52 seconds minus 39 seconds, which is 13 seconds in the shop. And I find myself, first of all, hoping he's the only customer, and secondly, that all he wants to do was buy a newspaper and pay in cash. Okay. Now we're going to look at two questions which involve the other aspect that was important, integration and differentiation. And now we've got this. A swimmer swims with velocity v, and we have this expression for their velocity, where k is a constant we haven't yet found. But we are given various information. I think we would assume that they start at time 0. We know how long it takes to do one length, and we're told the maximum speed in order to find when k equals 2. Okay, let's see if we can sort that out. So the equation for the velocity, 0.006 t squared minus 0.18t plus k, and the first thing we're asked for is the acceleration. So acceleration equals dv by dt. So we'll differentiate, bring down the power, so that's 2 times 0.006, which is 0.12, and here, if it's just a multiple of t, it's just the multiple, and differentiating k gives us 0. So there's our expression for A. That's the acceleration in terms of c. And now, part 2, we're going to find something about minimum speed. And the minimum of anything is when the derivative is equal to 0. So if I want the minimum speed, I'm going to have to differentiate and set that equal to 0. Well, I've already differentiated and it gave me the acceleration. The minimum speed is going to happen when the acceleration equals 0. Therefore, the acceleration, which is 0.012t minus 0.18, must be equal to 0, which means 0.012t equals 0.18, adding 0.18 to both sides, and now dividing both sides by 0.012 gives me a value of t which is 15 seconds. Okay, so I've found when that happens from the information I was given. Now it says show k equals 2. Okay, what do I know? I know when t equals 15 seconds that the velocity is 0.65 meters per second. Let's substitute that into the expression I know for the velocity, as that contains k. So 0.006 times 15 squared minus 0.018 times 15 plus k must be equal to 0.65. Well, this works out to be 1.35 and the next part to 2.7. So those plus k must equal 0.65. So by a bit of rearranging, k must be 0.65 minus 1.35 plus 2.7. And conveniently, k works out to be 2. So that's good news because it confirms our equations are correct. Now let's look at the last part of the question. Express the distance travelled by c in terms of t and calculate the length of the pool. So we've got velocity and we need to find distance, so we're going to integrate that expression, and from the information that it takes 28.4 seconds to do one length, we're going to find the length of the pool. Okay, so x is the integral of the velocity with respect to time, which means x is the integral of that expression we saw, which I better write out again so we can check our working, and plus 2 because we know k equals 2. Okay, integrating then, we increase the power and divide by the new power, so 6 divided by 3 is 2. Increase the power, divide by the new power, so I'm going to get 0.09 when 0.18 is divided by 2, and here it's just 2t. Now we need to allow for there being a constant. However, what do we know? We know when t equals 0 that the distance travelled is 0, and looking at this expression, when x is 0, t is 0, t cubed is 0, t squared is 0, t is 0, and therefore we can see that in fact c is also going to be 0. So that's handy. I have my expression for x. Now let's put in the piece of information we know. When t equals 28.4, that's when we get to the end of the pool, and x is equal to 0.002 times 28.4 cubed minus 0.09 times 28.4 squared plus 2 times 28.4. Definitely going to reach for the calculator for this one, and we find x equals 30.022208. In other words, x is 30.0 meters to 3 significant figures, and I guess that means we're talking about a 30-meter pool. Okay then, on to another question. A particle is projected from a fixed point along a straight line. The displacement is given by this expression. Find the velocity and acceleration. So for part 1 we're going to differentiate twice. Then show that when the acceleration of p is 0, p is at 0. Okay, we can do that. Third part, find the values of t when p is stationary, in other words when it's not moving and its velocity is 0. We'll come back to part 4 when we've done the first 3 parts. Okay then, the particle moves with the following displacement. X equals 0.1 t cubed minus 0.3 t squared plus 0.2 t. Well, my first job is going to be to differentiate that to get the velocity and the acceleration. Velocity equals dx by dt, and that gives me velocity equals bringing down the power 0.3 times t squared minus bring down the power times 0.3 is 0.6, and take 1 off the power, t, plus 0.2t differentiates to 0.2. There's my expression for velocity. Next, the acceleration. For the acceleration, differentiate the velocity. So acceleration equals, bring down the power of 2, that'll be 0.6, and take 1 off the power, 0.6t, and we also get 0.6 from the second part. There's my expression for acceleration. And for part 2, well, when the acceleration equals 0, we've got to show the particle is at p. In other words, that x is 0. Well, let's use what we know. If the acceleration equals 0, then 0.6t minus 0.6, that's my expression for acceleration, equals 0. In other words, 0.6t equals 0.6, and therefore t equals 1. Okay, let's pop that into the expression above that we've got for x. X equals 0.1 times 1 cubed, that's 1, take away 0.3, sorry, just correct that, 0.3 times 1 squared, which is also 1, plus 0.2 times 1. Well, that all boils down to 0.1 minus 0.3 plus 0.2. In other words, 0.3 take 0.3, and my total distance x is 0. Therefore, the particle is at p. Okay, let's look at the third part of the question then. And the third part asks us, when is p stationary? So if p is stationary, that implies it's not moving, that the velocity equals 0. So I'm going to use my expression here for velocity and solve that equal to 0. So 0.3t squared minus 0.6t plus 0.2 equals 0. I don't much like it with all the decimals in, so the first thing I'm going to do is multiply through by 10. 3t squared minus 6t plus 2 equals 0. And I did that in the hope it would factorise, but I have tried and it doesn't factorise, but at least it gives me whole number coefficients to put into the formula. T equals minus b, which is minus minus 6, that's 6, plus or minus the square root of 6 squared minus 4 times a, that's 3, times c, which is 2, all over 2a, which is 6. So t equals 6 plus or minus the square root of 36, take 24, that's 12, all over 6. And don't go rushing and writing square root of 2 or something like that. Let's be careful about simplifying that surd. Okay, square root of 12 is the square root of 4 times 3. The square root of 4 is 2, and the square root of 3 is the square root of 3. So my answer in surd form is 6 divided by 6, which is 1, plus or minus 2 over 6, which is a third of root 3. Or indeed you might have simply gone straight for your calculators and got the two answers, 1.57735, etc., and 0.4226497. In other words, the answers are 1.58 seconds to 3 significant figures and 0.423 seconds to 3 significant figures. And there's the times when p is stationary. Okay, let's look again now at the question. At the instant when p first leaves the origin, a particle q is projected from the same point. At the instant, at the same time, when t equals 0 for this particle q, its position is 0. That's significant. And it moves on the same straight line as p. Well, there's going to be a collision. We've got something here about velocity, but they're going to collide when they're at the same distance from the origin. They're both at the same point. So I'm given velocity and I need to find out the distance. Let's start then by dealing with the velocity. For q, the velocity equals 0.2t squared minus 0.4. Well, I want x, and that's the integral of the velocity with respect to time. So x is integrating, I increase the power and divide by the new power. I don't want to write that as a decimal because it's going to be a fiddly one. And then 0.4 integrates to 0.4t, and I better allow for a constant. I'm going to call this one k because I used c elsewhere in the question. However, we do know that at time equals 0, the distance from the origin is 0. Because like p, it was projected at the same time. So looking at our equation, when t equals 0, x equals 0, so therefore k must be 0. So my expression then is for q that x is, now I'm going to multiply top and bottom of this by 10 simply because I don't want to write a nasty decimal, minus 0.4t. Well, that's for q, and I also know what's happening for p. I've got this expression which I found by integration earlier. And if I want the particles to collide, then their distances from the origin must both be the same. Let's equate those and see what we find. So then, for the collision, we've got the following: 0.1 t cubed minus 0.3 t squared plus 0.2 t, that's the displacement for p, equals 2/30 of t cubed minus 0.4 t. So I'm equating those two sides. Well, the first thing is I don't much like all the decimals, so I'm going to multiply through by 10. That gives me t cubed minus 3t squared plus 2t equals, well, multiplying this by 10, I get 2/3 t cubed minus 4t. That hasn't eliminated all the fractions and decimals, and as there are only integers in the final equation that I'm asked to show, I'm going to make sure there's all integers before I go any further. So the next thing I'm going to do is multiply through by 3. 3t cubed minus 9t squared plus 6t equals 2t cubed minus 12t. Now I'm going to get it all onto the left because that has the largest multiple of t cubed. Subtracting 2t cubed from both sides gives me a single t cubed here. I've got only the minus 9t squared, but I'll need to add 12t to both sides. And there we go. That's the expression I was asked to derive. So let's go further now and find the value of t when they first collide. Well, if that's equal to 0, I can take out t squared minus 9t plus 18. And happily this does factorise. I want factors of 18 which add to 9, and those are 3 and 6. And then the signs either have to be both positive or both negative. Well, they're clearly going to be both negative to make the minus 9. And that gives me 3 solutions: t equals 0, t equals 3, and t equals 6. I'm not surprised about the t equals 0 because they both started from the origin at the same time. But I'm asked to find the value of capital T, which is when they first collide. So capital T must be 3 seconds because that's the first time after the motion started when they're both at the same distance. Okay, well, I hope that's been a helpful reminder about everything to do with kinematics of a particle in a straight line and choosing the right Suvat equation. All the best.